Hello, this is Young-Si Kim. Welcome to Signal and System class. I would like to briefly introduce about this class. The main textbook will be used at this lecture note. The lecture note will be provided through the LMS system. If you see this announcement, then you can access this lecture note and you can see that. So this is it. This lecture note developed based on the signal system written by OpenAIM. I think that this lecture note will be enough to follow this class, but if you need more materials, then I recommend to see this textbook. And the rubrics for the evaluation of this class is looking like this one. The attendance is 5 points, midterm 20 points, and the final 30 points. We have 2 quizzes. Each quiz will 10 points, the total 20 points. And there is assignment that will be 25% the point. The detailed evaluation policy refer to the syllabus. I recommend to refer this site. This one is OCW. Okay, let's see. Okay. If you refer this site, you can see the lecture given by the OpenAIM. There is another lecture note. It is not the same of my lecture note, and you can see the video contents. So if you need additional the materials to study, I recommend to refer this site. And also in this class, we are using Python, and sometimes we are using MATLAB. So to study the Python, you can refer to this site. And also the signal and system can be applied to the communication and control. Those topics applied the signal system will be introduced here to these two, for these two OCW lecture that is also related to this class. The textbook consists of 11 chapters. The first chapter related to the signal and system. What is the continuous and discrete signal and systems? The definition and terminology are introduced here. The second chapter is defined the linear time invariant system. What is the property of that one? What is the definition of LTI system? That is the chapter 2. And first 2 chapter gives a very important concept. Or in case of a LTI system, it is important our assumptions. All the systems or signals are assumed at the linear time invariant. Chapters 3 to 5, the consecutive 3 chapter covers the Fourier transform, which is related to that the Fourier transform. Chapter 3 explains the Fourier series representation of signal, and chapter 4 covers the Fourier transform of continuous signal. Chapter 5 for the discrete time Fourier transform will be covered. And chapter 6 is related to the Fourier transform. The magnitude and phase of Fourier transform are plotted in some special way. That is the topics of chapter 6. And chapter 7 is a sampling theory. Sampling means that how to convert a continuous signal to the discrete one, or discrete time signal should be converted to the continuous way. How are we going to do that? That is the topics of chapter 7. Chapter 8 is a little special. It's related to modulations. Especially in communications, we are using the AM, PM, or some special modulation we are using. How we can describe the modulation systems. That's the topics, chapter 8 topics. And chapter 9 and 10 is related to each other. The Laplace transform is one special transform quite similar to Fourier transform. Just switching the basis function, then we can do the Laplace transform. Basically, it is not that much different from Fourier transforms. Laplace transform is a continuous version, but the discrete version of Laplace transform is this transform. This big difference between Laplace transform to the Fourier transform is a region of convergence. Reason of convergence is related to the Laplace transform. This makes it special. Okay, 9 and 10 is also very important to characterize systems, to understand the system property by use of these transfer functions. Laplace transform described by its pole or zeros in the transfer functions. That will be topics of chapter 9 and 10. And the last chapter covers a feedback system. Here the keyword is feedback. In case of feedback, we always consider that the stability of the system. To check up the stability, we refer to Lutrok's technique or Nyquist or gain of phase margin. One of these three techniques are used, or some of them simultaneously considered to characterize the system stability. I just briefly introduced the whole chapters of our textbook explained in these books. Okay. This part explained our weekly schedule. In the syllabus shows up these topics. First week we will study the signals. It is in the signals will be introduced some basic concept for what is the signals, how to handle that one. That is the topics of week 1. The right hand column shows that the corresponding chapter, like shown here. This chapter 1 is this one. So if you interpret the right hand side columns, it's just directly related to the chapters of the textbook. Okay. So week 2, we will talk about the test signals. To characterize a systems, we are using some special signals. What kind of signals are used? Why we are using that signals to characterize the systems? That is the topics of week 2. Week 3, we will study the convolution in the LTI system. The convolutional operation is very important when we handle signal in systems. What's the meaning of convolution, and also we need to know how to implement the convolution. Okay. The next week we will study the Fourier series and Fourier transform. This is very important. How to converting from the time domain or space domain signal to the frequency or momentum domain. How to transform that one. So chapter 4, 5, 6, the week 4, 5, 6, we cover the Fourier transform. This is very important. The whole semester. This is the key concept. So we will cover for 3 weeks Fourier series and Fourier transforms, and then we move on to the filtering and Laplace transform. Laplace transform is closely related to Fourier transform, so we assign just after Fourier transform, and we assign the Laplace transform here. And I said that the Laplace transform has some reason of convergence. Reason of convergence interpretation is very important to consider the residue theory to taking the inverse Laplace transform. You know what? After studying the Laplace transform and inverse Laplace transform, you may know that the inverse Laplace transform is complex domain integration is required. In the complex domain integration, there is some special integration method exists. That's the residue theory. By use of residue theory, we taking the inverse Laplace transform. In Laplace transform and inverse Laplace transform we're covered. And then we will study the stability and the second system. If you know that the Laplace transform shows that the system transfer functions. In the transfer function, they have poles or zeros. If you inspect the location of the pole or zeros, then you can determine the stability of the systems. That is studied in week 11. And week 12, we will study feedback system and also sampling theory. Sampling theory is very important. Sometimes we allow more times for the sampling theory. And the next week, we will study interpolation, discrete time system, and discrete time Fourier transform. We also study the Fourier transform at here. We can apply the same technique to discrete time systems, and also Laplace transform applied in discrete time system, that becomes the G transforms. That's the whole topics that we cover in this semester.